Hi all. Today we'll be discussing the LeetCode problem of the day, number of smooth descent periods of a stock. So here you're given an integer array prices denoting the daily price of a particular stock. Now a smooth descent period of a stock consists of one or more contiguous days such that the price of each day is uh, lower than the price of the previous day by exactly one. And the first day of this period is exempted from this rule. So suppose we have prices, we have stock price for 7 days, and if we pick suppose these three contiguous days, now in these three, uh, let's say the prices are 4, 3, and 2. So by definition, the price of each day should be lower than the price of the previous day by exactly one. And the first day is exempted. So for the first day, you won't check the rule. Now for the second day, the price is exactly one less than the previous day. And for this as well, the price of the stock is exactly one less than the previous day. So this contiguous block is a smoothest descent of this of the stock. So at the end, you just have to count the number of smoothest descent periods. Now let's see the input. First example, we have 3, 2, 1, 4. So for this, we can see that uh, this only the stock on price 3 is a smoothest descent because by the first day rule, this is exempted from any further checking. So we have the descents as follows. One is 3, then next we have 2, next we have 1, next we have 4. After that, you can have 3 and 2 as the contiguous smooth descent period. 3 and 2 because 2 is less than 3 by exactly 1. Then you can also have 2 and 1. Then finally, you can have the entire 3 to 1. So 3, 2, and 1. Because here as well, 2 is exactly less than 1 less than 3, and 1 is exactly 1 less than the previous number, which is 2. So in total, we have 1, 2, 3, 4, 5, 6, 7. So the answer is 7. Now let's see the second input. We have 8, 6, 7, 7. Now in this example, we have only 8 as a descent period, smooth descent period. And we have only 6. And we can have only this 7. And we can have only this 7. After this, we can see that no other contiguous days will follow this rule. So the answer will be only 4 for this. Finally, let's look at the last example. We have the stock price for only 1 day. So only this one will contribute to the answer. So the answer is 1. Now coming to the constraints, the number of size of the array will be up to 10 power 5 and the prices can be from 1 to 10 power 5. Now let's go over the approach. So suppose we have this input of size 5. So for size 5, we will have total 5 into 6 by 2, which is 15 subarrays possible. So these are all the 15 subarrays possible. And out of these subarrays, we can individually find out which subarray is smoothest descending period. And if we count it, that will be our answer. So in this example, all the subarrays of size 1 will contribute to the answer. And here 3 and 2, it's smoothly decreasing. 2 and 1 is also smoothly decreasing. 1 and 5 is not. So I won't it. Next we have 5 and 4. Then we have 3 to 1. 2 and 5 is not a smooth one. No, also 1, 5, 4 is not. Next 3, 2, 1, 5 and 2, 1, 4, 5. 3, 2, 1, 4, 5. Yeah. So out of 15 subarrays, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So out of this, 9 will be our answer. So if we list out all possible subarrays and for each subarray, if we iterate on it individually to check whether if it's a smooth descending period or not, the total complexity will be order of n square. N square because we have total n square subarrays and into order of n for checking whether if it's a smooth or not. So by this approach, you will have total complexity of order of n cube. But we saw the constraints that n can be up to 10 power 5. So order of n cube will fail. We somehow had to reduce the complexity. So if we look at the input, we can see that the entire input can be split into the smoothest consecutive periods. So we can see that 3 to 1 is a chunk of smoothest descent period. Then after that, the price is increasing, and then we have 5 and then 4. So here also it is decreasing just by 1. So this is a part. Now we know that 3 to 1 is a smoothest uh, descending period. So once we know that a subarray is a smoothest descending period, so out of this subarray, we divide it into all possible subarrays. Each of the subarray will also be a smoothest descending period because the entire array itself is decreasing by 1. Suppose if we list them out, we have first 3, then 2, then 1, then we have 3, 2, we have 2, 1, and finally we have 3 to 1. So these are all possible subarrays of this 3 to 1 array. So we can see that all of them are smoothly descending periods. Also, we can see that by this we have covered this, this, and this. So we have covered all these 6 subarrays in our original answer by just taking all possible subarrays of this 3 to 1 block. So now let's look at the other one, which is 5 and 4. So 5 and 4 is also a smooth descending period. So if we take all possible subarrays of this, it is 5, 4, and then 5, 4. Now if we look at this in our all possible subarrays, 5 is included, 4 is included, 5, 4 is also included. So we can see that if we just split the entire array into smooth descending periods and count how many subarrays can be formed for each of this part and add them all, that will be our answer. So for this subarray, the size is 3. So total number of subarrays will be 3 into 3 plus 1 by 2, which is 3 into 4 by 2, which is 6. And for this, it is 2 into 3 by 2, which will be 3. So if we add 6 plus 3, we'll get the answer as 9. So the main approach is simple. We just have to iterate on the array until we have a smoothly descending period. So suppose our current block has smoothly descending period up to 4 numbers. And after that, once the next number is not following the smooth descending period rule, then we just compute the answer for this block. And from this element, we'll start the new block. And we'll just keep repeating this for the entire array and add up all of them. And that will be our answer. Now let's code the approach. So after we code it, we'll do a dry run on this example. So first let's declare the variables answer equal to 0 and initially count will be 1 because we will start iterating from index 1. So count is equal to 1 is representing 7 so far. So now we'll start the iteration equal to 1 and okay. So far we have iterated on I equal to 0 and we have counted the 7. So that's why the count value is 1. And next we are starting from I equal to 1. So now we check whether index I equal to 1 is exactly one value less than the previous value. So if prices of I minus 1 minus prices of I is exactly equal to 1, then our count increase. But in this example, we can see that price of I minus 1 is 7 and price of I is 4. So 7 minus 4 is 3. So that means right here only it breaks. So let's keep the variable count. So initially count was 1 and answer was 0. So at I equal to 1, we go to the else case. That means so far count equal to 1 represents there is one length contiguous subarray which is smoothest descent period. So now we'll just find all possible subarrays of this size 1 and add it to our answer. So in our answer, count into count plus 1 by 2. Just put the brackets. Yeah. Now once we do it, we have to reset the count value to 1. Count equal to 1. Count equal to 1 indicates that we are starting a new subarray at this point, I equal to 1. So next, when we move to the next iteration, when I equal to 2, we see that price of I minus 1 minus price of I is exactly equal to 1. So from 4, it is exactly decreasing by 1. So we increase the count. So count will become 2. Also in our answer, we previously made 1 into 1 plus 1 by 2. So answer will be 1 so far. Yeah. So now count equal to 2. So that means we have found 4 and 3, which is contiguous of size 2. Next, we continue our iteration. So we move to the next element. Again, we see that this 2 is exactly 1 less than the previous value. So again, we go to the if case and we increase the count. So now count is becoming 3. Now we move to the next element. Now we see that the previous value minus the current value is not equal to 1. So here the contiguous part breaks. So if you look at our count is 3. So that means there is a contiguous segment of size 3. Now in this segment of size 3, we have to find out all possible subarrays and add it to our answer. So 3 into 3 plus 1 by 2, which is 6. So in our answer, we'll just add a 6. And once we do it, we'll reset our count value to 1. So count becomes 1. And it indicates we are starting a new subarray from the current value. Now after this, the I moves forward. Yeah, I moves forward. And okay, in this example, I think this has to be 5 so that it's a contiguous decreasing subarray. Yeah. So when we are at 5, so price of I minus 1 minus price of I is exactly equal to 1. So 6 minus 5 is exactly equal to 1. So count will increase by 1. So count becomes 2. And then you come out of the loop. So once you come out of the loop, your answer is only 7. That means you have computed the answer only for the first 2 contiguous parts. So you missed the calculation for the last part. So to do that, once you come out of the for loop, so whatever value the count was previously, you again have to compute it and add it in your answer. And at the end, just return answer. Okay, let me submit. Yeah, and it works. Finally, let's do the time and space complexity analysis. So for the time complexity, since we are just iterating on the array ones, it will be order of n. And for the space complexity, it will be constant because we are not creating any array. We are just using 2 variables and just the iterator I. I also have the code in Python if anyone wants to view it. I'll add this in the description as well. And let's catch up in the next video.